Hey guys, welcome to Impulse and Momentum. We're going to be going through the notes today, and we're going to look at impulse and momentum and take some notes. But you can do this at your own pace. If you need to stop and write the notes down, and you're taking longer than the person next to you, that's totally fine. Take as long as you want. If you want to go back and replay the video later to review for your test, then you can do that anytime you want on my website. So let's start. Let's look at impulse and momentum. So have you ever wondered why golfers and bowlers follow through? Have you ever heard that term before? Why skydivers have to bend their knees upon impact? Or why falling onto something that's wood or carpet or falling into a swimming pool hurts less than falling onto cement? Why are all those things true? Well, think about it. Remember Newton's first law, which is the law of inertia, says that the inertia from that bodies in motion will stay in motion, and bodies at rest will stay at rest unless some force causes them to change. Now, inertia is the resistance of an object to changing its motion. The bigger that object is, or the faster it's moving, the more inertia it has. And so when we're specifically talking about things that are moving, we're talking about momentum. Okay, so momentum is inertia, it's a resistance to change what they're doing, but it's specifically for things that are moving. Objects that are not moving don't have momentum. So momentum of a body is equal to the product of its mass and its velocity. The more mass something has, the bigger it is, like say a train, it would have more momentum than something smaller like a car. And also the velocity is going to change the momentum. The faster it's going, the more momentum it has, which is why objects that are not moving don't have momentum. There's no velocity. So is momentum a vector or a scalar? If you look at it, momentum includes velocity, which has a direction to it. Velocity is going in a certain direction. So as a result, your momentum will also be in a certain direction. You'll have momentum forward, or momentum backwards, or to the left, to the right, north, south, east, west. And then the next one is, what are the units of momentum? Well, mass is kilograms, and velocity is meters per second. Boringly enough, the units for momentum are kilogram meters per second. Nobody's name, until you discover something cool and name it after yourself. Nobody's name, just kilogram meters per second. So here's an example. We've got a 50 kilogram cart rolling down the hallway at 5 meters per second. How much momentum does it have? Well, remember, momentum is mass times velocity. We just wrote that down. The mass is 50 kilograms. The velocity is 5 meters per second. So when we simply multiply those things, we get 250 kilogram meters per second. Impulse is very closely related, but just a little bit different. Impulse is a force that is applied over a period of time. And so we have both the units of force and we have time coming into play. So, again, boringly enough, the SI unit for impulse, if force is newtons and time is seconds, impulse is Newton seconds. That's it. Again, until you discover something great, name it after yourself. So, a batter that hits a half kilogram ball with a force of 200 newtons contacts that ball for 0.205 seconds. During that time that it's in contact, how much impulse does it have? Well, force times time is impulse. The force is 200 newtons. The time it's in contact is 0.205 seconds. We don't need to include the half kilogram ball. For this one, it doesn't matter. So our impulse that we apply is 41 Newton seconds. Look at those units, impulse and momentum. We said they're related. Do you notice anything, newtons and seconds and kilograms and meters per second? Let's kind of go back a little bit to Newton's laws of motion that we just finished. Remember the second law, F equals ma. Can we kind of rearrange that and see what happens? So F equals ma. Well, what's acceleration? Acceleration is velocity over time. So if we sub that in, force equals mass times velocity over time. So we can kind of simplify it and make it look like that. Force is mass times velocity divided by time. But I hate having things in the bottom, so I'm going to move that time around. So if we're currently dividing by time, we do the opposite, which is multiply by time. So we get ft equals mv. ft, we just wrote that down. F times t is impulse. And mv, mass times velocity, we just wrote mass and velocity down as well. So impulse equals momentum. They're the same thing. The impulse that you apply to something is equal to the change in momentum that you get. If you want to stop a car, it has a certain amount of momentum as it's traveling down the highway. You have to apply a force. That's the brakes. You have to apply them over a certain period of time, which is your impulse, and you change that momentum. You stop the car. So the longer you apply the brakes, the more change in momentum you get, or maybe the harder you apply the brakes, the more force, the more momentum change you get. But that impulse that you apply is going to change the momentum of your object. So let's think about it as it relates to sports. If you only have so much force, you're a human. You can work out all you want. You're only going to have a limited number of force to apply to, say, a baseball or a golf ball. How can you maximize the impulse that you can apply to something? Increase the time of contact. That's where the following through comes from. If you continue that swing, if you go with the ball, if you follow through on your swing, then you apply your force over a longer period of time and change that momentum more than if you were to just tap it. On the other side, what if you don't want a lot of force? Like, say, in skydiving, or boxing, if you don't want a lot of force, if you want to minimize the force on your body, how can you minimize force? You can increase the time of contact. So bending your knees upon impact, rolling with the punches, crumple zones in cars, you're applying that force over a longer period of time. So you have less force. That impulse that's changing your momentum, by the time being larger, can decrease the force. So let's talk collisions. Collisions is any time you have two objects interacting and they've made contact with each other. And this doesn't have to be something violent like a car wreck. It could be something as simple as pushing a shopping cart. Your hands are interacting with the handle of the shopping cart, and that is causing a motion. It's causing things to move. That's a collision. Anytime you run into somebody in the hallway, whether you hurt them or not, you're colliding. You have two objects that are interacting. And your collision results in some kind of force being applied to both objects. Remember Newton's third law, action-reaction. The force that you are applying to an object is met with a resistance force being applied back to you. So both objects are going to experience forces, and the forces are equal in magnitude, but opposite in direction. So one object, now we're talking about momentum again, one object is going to speed up, it will gain momentum. The other object would slow down, it would lose momentum. You push the shopping cart, you get a little bit of a resistance, you have to increase force to make both you and the shopping cart walk or move. So the shopping cart starts moving, starts gaining momentum where it previously had none, and you lose a little bit of momentum. You have to input more force over time. You have to increase your impulse to get the entire system to gain momentum. So think about like with a golf club and a golf ball. The golf club hits the golf ball. You don't really notice a big change in the golf club, but you notice a big change in the golf ball. The golf ball takes off at an enormous velocity. But that one, the reasoning for that, it's kind of hard to think that it's the same force applied to both in this situation, because you think, well, gosh, look at the ball taking off, and the golf club is still sitting here. But think also about Newton's second law, F equals ma. They both had equal and opposite forces, but your ball has a much smaller mass than the club. So your least massive object will receive the greatest acceleration. The most massive object will receive the least amount of acceleration. So we can incorporate that F equals ma with our action-reaction, our equal and opposite forces. So when we have this interaction, you've got two objects that are colliding. Their momentum is going to change somehow. The law of conservation of momentum states that in an isolated system, we're going to ignore friction for right now, we're going to ignore air resistance, all the other things that come into play. We're just going to look at the two objects and their momentums. When you have a collision in an isolated system, the total momentum before the collision is equal to the total momentum after the collision. You might have just swapped from one to the other. So your formula down here in red means write it, your formula down here in red says that the momentum of your first object before the collision plus the momentum of your second object before the collision is equal to the momentum of object A after the collision plus the momentum of object B after the collision. Your total is going to be the same before as after. They're just going to swap places. You have two types of collisions, elastic and inelastic. And the difference between the two depends on whether your objects remain independent or whether they stick together. So an elastic collision is when each object remains independent. Think of it like playing pool. You hit the white ball, the cue ball, it rolls across the table, it hits the red one. The red one takes off in another direction. They remain independent after the collision. They're not going to stick together. So your momentum of each of your cue ball and your red ball are different, and they're remaining independent. You don't calculate them as one object after the collision. So look at the formula down here. Your mass times velocity, that's momentum. Mass times velocity of object A before the collision, plus the mass times velocity of object B before the collision, is equal to mass and velocity of the first object plus the mass and velocity of the second object after the collision. Their total is going to remain the same. So let's look at a practice problem to see how that's going to play out. We've got a half kilogram ball traveling at 6 meters per second. It's colliding head-on with a 1 kilogram ball, moving in the opposite direction at a speed of 12 meters per second. The half kilogram ball is going to bounce backwards at 14 meters per second after the collision. Find the speed of the second ball after the collision. So how fast is it going post-collision? Well, let's start with our formula, just setting it up. mv of A, mv of B before the collision equals mv of A after the collision plus mv of B after the collision. We're going to sub in what we know. We know the mass of the ball and how fast it's going, the mass of the second ball, how fast it's going. Now notice the negatives. We have to use the negative and positive in order to establish the direction that it's going. So that's the reason for the negatives. We go ahead and simplify by multiplying. We add together the things on the left side of our equation, and then we're going to need to take away that 7 kilogram meters per second from the other side, so we'll subtract, which in this case, with it being negative, means we'll actually be adding. So we get negative 2 kilogram meters per second equals 1 kilogram times the velocity of ball 2. Divide by that 1 kilogram, and our ball is going negative 2 meters per second. Inelastic, post-collision, they're going to stick together. So pause here and write this one down. You notice that the mass and velocity before the collision are going to be equal to the mass and velocity after the collision, but notice our two objects are together, counted as one. And we have a new velocity that they're both moving at together. So if we've got, say, instance, freight cars coupling, they each have a mass of 30,000 kilograms. They're colliding. One was moving, one was not. And they stick together. What was their final speed? We go ahead and set up our problem using the previous equation. We fill in the numbers that we know. Simplify. Okay, remember to multiply. 30,000 times 0 is 0, so it'll go away. Divide by 60,000, and we get a velocity of 1.1 meters per second. Okay? Now, that is it for collisions, impulse, and momentum. The good thing is about this video, you can always go back. You can repeat, you can play it again. If you're still having trouble, come and get me, and I'll try to explain some things in further depth. But I wanted to spend more time on applying this and less on just taking notes, which is tedious. So hopefully you can do this on your own, and if you need anything, let me know.